This video is an introduction to chemical equilibrium. Equilibrium mixtures result because reactions don't always go only forward, they can go backwards as well. Equilibrium is based on the rate at which a forward reaction occurs equals the rate of the reverse reaction. So for example, in this reaction, the forward reaction's rate would be Kf times the concentration of N2O4. And the reverse reaction's rate is going to be Kr times the concentration of NO2 squared. Remember, at equilibrium, the rate of the forward is going to equal the rate of the reverse reaction. And so if I replace these into this equation, it should look like this. Kf times the concentration of NO4 equals Kr times the concentration of NO2 squared. Kf and Kr are constants, so I'm going to go ahead and move variables so the K's are on one side and the concentrations are on the other. Now you will notice that Kf divided by Kr, because I divided both sides by Kr, and divided by both sides by N2O4, and I get this constant. And here is going to be, the K's are going to be equal to my equilibrium constant. And this is how you would pretty much set the equation up. It is going to be the products, the concentration of the products to whatever exponent, divided by the concentration of the reactants to whatever exponent. So let's now understand what the K value actually represents. First and foremost, K is basically the ratio between the products and reactants. So, if K is larger than 1, this means that we have more products than there are reactants. It means the reaction favors going towards the products versus going backwards to its reactants. If K is less than 1, well then, at equilibrium, there is more reactants than there are products. So therefore, that means that the reaction is favored going towards the reactants instead of the product. Okay, let's go ahead and remind ourselves. If there are more products than there are reactants, that means K is going to be greater than 1. If there are less products than reactants, the K is going to be less than 1. So we're going to look at these three and rank them from increasing Kc. So let's go ahead and look at the first reaction right here. The red represents the reactants and the blue represents the products. Right now we can totally tell that there are more products than reactants. This means that K is going to be greater than 1. Okay, in this example here in the second box, we can see that the green represents the reactants and the yellow represents the products. There are substantially more green than there are yellow, so that means that there are more reactants than products. So this one, the second, is that K is less than 1. Now we can go ahead and look at the final example where blue is the reactants and red is the products. Here, again, there are more products than there are reactants. So this means that K is also greater than 1. Now, if we look at this, how do we know between the first and the third, which one is going to have a greater K? And that's based on the ratio. Since there are more products than in the third than there are in the first, this means that the third is going to have a greater K than the first. So I would rank this from 2 being the least, 1 being the second most, and the third being the most Kc. Now this time, let's go ahead and calculate the Kc for each one of these boxes. We're going to assume that the container is 1 liter and each one of these spheres represents 1 mole. So let's first calculate the concentration for each one's, the reactants and the products. In the first box, the reactants, there are 1, 2, 3, 4 moles in a 1 liter container. Therefore, the concentration is 4 molar. And for the products, there are 1, 2, 3, 4, 5, 6 moles in the 1 liter container. Therefore, there's 6 molar concentration of the products. And if we find the Kc, that is the concentration of the reactants over the products. My mistake, I mean the concentration of the products divided by the concentration of the reactants, which is 6 divided by 4, which is equal to 1.5. And since this is 1.5, that is greater than 1, this does show that the reaction goes forward to the products less than the products going to the reactant. So this is shifting towards the right. For number 2, we're going to go ahead and count the reactants. 1, 2, 3, 4, 5, 6, 7, 8, 9 moles per 1 liter, which means that it is a 9 molar. For the products, there's only 1 yellow, so it's 1 mole over 1 liter, which means it's a 1 molar product. And so if we go ahead and plug this into determining Kc, you will have 1 divided by 9, which is equal to 0.11. Now this is less than 1, so this goes ahead and definitely shows us that there is a favor of the products going to the reactants rather than the reactants going to the products. And for the final example, we can see that there are 1, 2 reactants, which means that there are 2 moles in 1 liter, which means there's 2 molar concentration of the reactants. And for the products, there are 1, 2, 3, 4, 5, 6, 7, 8 moles. So there is an 8 molar concentration of the products. And so if we look for the equilibrium constant, it will be 8 divided by 2, which is 4. And this definitely does show us the ranking we did in the first part is correct, where 3 had the largest Kc value and 2 had the smallest Kc value. The equilibrium constant, Kc, does depend on the direction in which you write the reaction. So for example, I have N2O4 going to 2NO2 versus 2NO2 going to N2O4. Although they are both equilibrium, written in equilibrium because of the double arrow, the Kc is written out, the Kc expression is written out as such. In this expression, you can see that Kc, you have NO2 squared divided by N2O4. In this case, NO2 squared is on the numerator and N2O4 is in the denominator. In this expression, you can see that N2O4 is now on the numerator while NO2 squared is on the denominator. They are reciprocal of each other. So if I take this equation and I take the reciprocal of it, which means I take this and divide it by 1, I should come to this expression. So what if Kc for this side is equal to 0.212? I can just go ahead and write for the reciprocal in order to get the value for this. I would just take 1 divided by 0.212, and that is equal to 4.72. Therefore, the reaction that goes from 2NO2 to N2O4, the Kc value is going to be 4.72. Try this on your own. At 25 degrees Celsius, the equilibrium constant is equal to 1 times 10 to the negative 30 for nitrogen gas reacting with oxygen gas to form 2 nitrous monoxide. Determine the equilibrium constant for nitrogen monoxide decomposing to nitrogen gas and oxygen gas. Pause here and work it out, and the final unpause to find the final answer. This concludes the introduction part to chemical equilibriums. You may move on to part 2 video.